So here we are with our first work problem. This is a pumping problem. We are going to use an integral to figure out how much work it takes to pump all the water out of this tank. This is a pretty standard work problem type. It's usually pumping something or lifting something somewhere. And the reason for that is this formula right here. Work is equal to weight times distance. This is the definition of what we mean by work. And this is pretty intuitive. You know, if I have to lift a 10-pound weight 10 feet up, I'm going to do 10 times 10, which is 100 pounds, or foot-pounds of work, rather. We measure work in foot-pounds, if the units of weight are pounds and the units of distance are feet. And in this case, it just happens that they are. We are looking at how much work it's going to take to pump all the water out of this tank here, which you can see has a base of, not really 8, it has a length of 8 feet. It's kind of this prism-shaped tank that is 8 feet long, and the faces of this thing are these triangles that have a height of 3 and also a base of 3. And this thing is full of water. We have to pump all of this water up and out of this spout here, which is 2 feet high. And the idea is that the whole tank is full of water, but the spout is not. And so Unlike that example with the weight, it's not quite so simple to compute how much of this how much work it's going to take to pump all this water out, because at any particular level, so at some distance y here from the bottom, not only is the amount of water that we have to pump, so I'm looking at this kind of green rectangular prism here, this what we call a cross section. At a particular height, the amount of water that I'm going to be pumping out is going to depend on that height, and also the distance that I have to pump it is going to depend on that height. So both of these things are varying continuously as I move from the bottom of the tank to the top, and that's why we're going to use an integral for this. So before we do that, let's sort of review, because I think it's really important to stress that the process in all of these integrals is the same, right? You should always be thinking the same stuff. What is changing? What is not changing? What is varying from where to where? You know, what are the things I'm adding up? We're thinking very hand-wavily about integrals as infinite sums of infinitesimal objects. And what are those objects? I mean mathematical objects, not physical objects, by the way, because in this case, the objects that we're adding up are work, which is not physical, it's an idea. In the case of, as we've already seen, area integrals, it is kind of a physical object, it's areas, but let's just review quickly. We're thinking of the integral from a to b, f of x dx, the area under the graph of f in between a and b. We're thinking of this as an infinite sum of these infinitely thin rectangles, which have a height of f of x here, and an infinitesimal width of dx. And so what's varying is the x, it's going from a to b. What's changing as x changes is the height of the function at the point, the f of x. What's not changing is the dx, it's constant. And we kind of think of it as this infinitesimally thin line segment with varying height sweeping out the area as it moves from a to b. And so taking this infinite sum of infinitesimally thin areas, of infinitesimal areas, that gives us this total area. And so that's the idea behind that. Coming back up here, we're going to do something similar. And by the way, I probably should have, to go back and forth too much, but we always began with sort of a partition, right? We sort of chopped up the interval into bits, and then we took Riemann sums and stuff. But the point is that without talking about limits and the sort of more analytical look at it, we're going to kind of think of this as in this picture right here, that I've kind of, and I'm back to Eraser again. By the way, I'm using a different program. You've probably noticed this one is I think better for our purposes. You can do stuff like scroll and stuff, many things which make the videos less annoying. The one thing that hasn't changed is that the pen still turns to an eraser randomly for some reason. So again, I'm sorry about that. Please bear with me. But I'm kind of thinking about this as chopping up, taking the face of this triangle and saying, okay, I'm going to chop this up into infinitely many that's not supposed to be a circle, infinitely many, and this is not cooperating. I'm just gonna make this not a perfectly straight line there. Infinitely many of these infinitely thin slices. So this thing here would correspond to this thing that I'm looking at there, and then use the integral to add them all up. So that's the first thing that I'm noticing, is that I'm going to have to integrate from, and my thing is gone again. I'm going to have to integrate from 0 to 3. And by the way, this is I think one of the big points of confusion with problems like this is, and this is certainly the question I think most students ask and that I asked. That's a little bit big for the spout, I think, which is why, if I'm lifting the stuff from the ground, the point where I start lifting is at the bottom, or pumping, I'm lifting it up to this thing. This is 2 above the ground, and this is 3 above the ground. Why am I not integrating from 0 to 5? A lot of people want this integral to be rather the integral from 0 to 5 of something, and it seems like it should be. But if we think about sort of what we're doing here, how we're thinking about this, just like I was adding up those infinitely thin area bits to find the area under the curve, here I'm thinking about this as adding up infinitely many infinitesimal units of work. And each unit of work that I'm adding up is going to be the weight of this green thing, this green cross-sectional thing, which we're going to compute in a second. So the weight of that times the distance that I have to lift it. And what is that distance going to be? Well, if this is at a height of, I can actually do that one straight. If this is at a height of y feet off the ground, well, how far do I have to lift it from y to get it to 5? I have to lift it 5 minus y feet. So that's where the 5 comes into this. But if we think about this again, what am I lifting? What is changing? Well, my sort of cross-sectional thing here, my purple thingy, it's actually varying from 0 to 3. It's starting at 0 and going up to 3. And at each point, I'm saying, okay, how much work do I have to do to lift this bit here to the top? And I figure out how much it weighs, and then see how far I have to lift it. So what the 5 is doing is actually not contributing to the bounds of integration. It's not, now that I want the eraser, I can't have it. It's not contributing to the bounds of integration. It's contributing to the amount of work that I have to do at a particular point. So if we looked at this picture, the 5 would be kind of contributing to this part of it. The amount, the area at the point, not where I'm integrating from, but what I'm adding up at that point. And we'll see exactly how that works in just a second. But that's the thing that usually sort of confuses people. I know it confused me when I did this the first time. So let's actually start to build this integral. And again, I think that building these things step by step is a really good way to do it, because you see the commonalities between the different cases, right? Where am I integrating from? And then at each point when I slice it or take the cross-section, what is the quantity that I get there? What is the object that I get there, the infinitesimal object? There's always going to be this infinitesimal here. There's going to be, in this case, a dy, and I picked y, by the way, just because we're going vertically from bottom to top. It could be x, it doesn't matter, but that's always going to be in there. And then I just have to figure out, and I figured out where I'm integrating from already, from 0 to 3, and now I have to figure out at any particular point where I stop, any particular y value here, what is the unit, the infinitesimal thing that I'm going to be adding at that point as y goes from 0 to 3. And to figure that out, well, I think about the question. It's work, so weight times distance. So let's sort of down here start constructing the object using that. I know that the distance at a point y, I've already figured that out. The distance at the point y that I have to haul the thing or pump the thing is going to be 5 minus y. I know that water weighs 6.25 pounds per cubic foot, so I'm going to need a 6.25 in there. I already have the dy, I'm back to the eraser again, the dy, but I'm missing something here. And what is that? Well, that's going to be the volume of this cross-section thingy. The weight is the this 6.25 came from water weighing 6.25 pounds per cubic feet. Now I need to think how many cubic feet at this point of water do I have? And for that, I'm going to go down to first here and then back up to that second picture. So this is the cross section blown up at a height of y, and I need to figure out the volume of this thing. So it has an infinitesimal height of dy. We've already said that. We've already picked that. It's fixed. It has a length of 8, as you can see here. That was given to us by the question. But I need to figure out how wide it is. I need to figure out this length here. And I need to figure out this length because that's going to give me the total volume. It's going to be 8 dy times the length. I need to figure that out at the particular height y. So when I go up from 0 to y here and stop, I need to figure out at this, once I've gone up y, how wide is the cross section that I'm taking at that point? What is the width of this thing here? And the way that I do that is, you might have guessed, because this thing has triangular faces, I'm going to use similar triangles for that. I'm going to go down to this picture. So I pull the face, this big triangle out here, and I get this picture, which is going to help me. Actually, let me scroll up a little bit because that's going to be kind of distracting. Okay, so I have here my face of the tank pulled out. It has height 3 and base 3, and then I've gone up this y distance, and I'm trying to figure out what is that cross sectional width, that x value here. And the way that I do that is I look at, of course, this similar triangle yonder. And I know that because these triangles are similar, I got this little one by just popping it out by cutting the big one perpendicular to the height here, and pulling this thing out. So they're going to be similar. And what does that tell me? That tells me that the ratio of the sides has to be the same. So that tells me that I'll do it in the same colors here. The base 3 of the big triangle divided by the height, which is also 3. This, I'll maybe do the equal sign in pink. This has to be equal to the base of the smaller triangle, x, divided by the height of the smaller triangle, which is y, and maybe let me stick with this nice neutral pink for the operator signs, although I did the other division sign in orange. Let me fix that for consistency. There we go. Okay. Now, of course, this 3 divided by 3, this is just 1. So I end up with 1 is equal to x over y, and I'm gonna stop this because it's getting annoying changing colors every time. 1 is equal to x over y, which means I can rearrange this and say x is equal to y. That's my if and only if sign, by the way, there. So x has to be equal to y. So that's convenient. When I go up y, I get a cross section, which is indeed y feet wide. That's what I have down here. And so the total volume of this thing ends up being 8 times y times dy. That's the volume of water that I have. And then let me just start reconstructing the integral down here. I'm going from 0 to 3, and I'm adding up. I have a volume of 8y dy, and I have the 6.25 pounds per cubic foot. And actually, let me move the dy over. And then I have to think, how far am I pumping this thing? Well, I decided I was pumping it 5 minus y feet, and then I multiply by the dy. And so, again, these together, the 6.25 pounds per cubic foot, times the 8y times dy, cubic feet of water that I have, times the 5 minus y feet that I have to lift this thing, that is what gives me the infinitesimal unit of work. And so what I'm doing here is going from starting out at 0 and going up to 3 and taking this infinite sum of infinitesimal units of work. And that, if I look at this, and I can finally fill in this picture up here in a minute, that if I look at this guy here, that's like starting at the bottom and at each one of these slices saying how much work do I have to do to lift it to the top, and adding all of those up as I go from 0 up to 3. And so just to fill in this integral that we started with, that gives me this 6.25. That's the pounds per cubic foot. And then I'm multiplying that by this dy, and then the 8y That's the volume, the 8y dy. This is the weight per unit of volume, 6.25 pounds per cubic feet, per cubic foot. This is how many cubic feet, and this is how far I have to lift each slice. So this is, looking at this picture up here, at this height of y, this thing is the volume of the slice, this 8y dy, this is the weight per volume, and then this 5y here, that is how high I have to lift it. And so we can think, again, it's not actually what's happening, it's a limit of Riemann sums, but we can think of this as starting at 0 and slicing this thing up into infinitely many, infinitely thin slices, and then computing how much work needs to be done to lift each slice to the top of this spout thingy here, and then taking the infinite sum of all these. Just like we thought of the area as an infinite sum of infinitesimal areas, and we thought of the volume of those solids of revolution as infinite sums of infinitesimal areas, whether it's the disks or the shells. We're doing the exact same thing here, except the infinitesimal units that we're adding up are units of work. They're bits of work, not bits of area or volume. And I'm just realizing, sorry, I have to be a little bit obsessive compulsive here. I realized that I wanted to shade this thing in the whole time. I have the one down there shaded, so, and now it looks a lot nicer. So just kind of pretend that from the beginning of the video, this cross section was actually nice and shaded in, just to show that it has some volume to it. I know this is kind of sad that I'm doing it at the end here. I would redo it, but it's been like 8 takes already. My dog kept barking. Okay, so that's it for the pumping problem. The next one is going to be a lifting problem, which is going to be even more abstract because we can't really visualize the same way that we had a cross section here. We're going to have a sandbag which is being hoisted, and as it's hoisted, there's a leak in it, and we need to figure out the total amount of work. But we can't really visualize the weight at a particular point the way we can here because it's not giving us a volume. But nevertheless, we're gonna see how to do that. We're gonna see that it's the exact same principle. So I will see you guys in that video shortly.